Alright, I'd like to work on this problem here where we have a conveyor belt that delivers a package to the top of a ramp. The package slides down the ramp and hits the wall at the bottom. The package at the very top of the ramp is, as I said, delivered by this conveyor belt. It has a speed that I'll call VB. The ramp has a length L and it's at an angle theta. And it has some friction on the ramp, so I can characterize the friction with the coefficient of kinetic friction mu k and mu s if we need it. And what I want to know is the speed at which it hits the wall at the bottom, and also the time it takes to get to the bottom. And we're going to make one assumption here. We're going to say that when it hits the bottom, it's moving at a speed faster than VB. So in other words, it starts at a speed VB at the top, and then when it hits, when it hits the wall at the bottom, it's going faster. All right, so here's my solution following what I call the problem-solving checklist. So the first thing I do is I draw a picture of the system. You see it up here in the upper left-hand corner. I got the ramp, I've got the block. I've labeled important parameters such as the length of the ramp, the angle of the ramp. I even got the speed of the block in there. I've defined a coordinate system, so s equals 0 starts right at there, and I'll let s parameterize my position as I've sort of written down here. So my position will be r equals s in the I hat direction. Again, s equals 0 is right at the top of the ramp. And I'm also defining some basis vectors for which I'm going to decompose my force vectors into. So E hat 1 would be tangent to the ramp, E hat 2 perpendicular to the ramp. Next thing I do, if you look in the problem-solving checklist, I list the quantities that are given. I'm given the speed of the block at the very top of the ramp. I'm giving the coefficients of kinetic and static friction. I'm giving L, the length of the ramp, and the angle theta. If you read the problem, you'll notice that I was not given the mass of the package. You might be concerned about that, but maybe it's not so bad. So I have not listed the mass of the package on here. I have also not listed G, that gravitational constant. G for me in solving problems is always given, so I can list it on here if I want to, or I can just leave it off, no problem. The next thing I do is I list the quantities that I want to find. I want to find what I'm calling VF, that's the speed at which the package hits this wall. I'm defining TF, the time it takes the package to reach that wall, starting at the top. Starting from the top. And I also list assumptions. So in the problem itself, we said that the speed at which it hits the wall, I call them VF, is bigger than the speed at the top of the ramp, VB. So I've got this inequality here. So the next item I have on the problem-solving checklist is to draw a free body diagram of the system. In this case, draw a free body diagram of the package sliding down the ramp. So here's my package. It has a weight pulling down. But I want to write this weight in terms of the basis vectors that I have here. So I got E hat 1 tangent to the ramp, E hat 2 perpendicular to the ramp. So that vector decomposition works out like so, if I got it right. I think I did. I've got a normal force. This is the force of the ramp pushing back up on the package. It is all in the perpendicular direction, or the E hat 2 direction, so I write it like so. And I have a friction force. Remember, the block is sliding down the ramp. And there's friction, so the ramp must be opposing that sliding motion. So the ramp has to be pulling upward and to the left. So that's in the minus, that's supposed to be in E hat 1 direction, not I hat. E hat 1 direction. So F in the E hat 1 direction. Now that I have a free body diagram, next thing I want to do is I want to draw a mass acceleration diagram. So let's put this in here as well. So this block, maybe it's hard to fit everything on the screen at the same time. So this block here is moving along a straight line, right? Moving along a perfectly straight line. So therefore its velocity and its acceleration have to be tangent to that ramp. It cannot have any component of velocity or acceleration perpendicular to the ramp, again, because it's a straight line. Now, according to my assumption, VF, the speed at which it hits the wall, is bigger than VB, so therefore the block has to be picking up speed as it's sliding down. So I'm thinking that this acceleration is in the positive E hat 1 direction. Again, this is supposed to be E hat 1, not I. Jeez. But what's important here is that it's tangent to the ramp. So I got MA in the E hat 1 as my mass times acceleration. To solve this problem, I'm going to use Newton's second law, so I state that expression explicitly right here, right? I say Newton, which is the sum of the forces equals mass times acceleration. Let me scroll down just a bit. Actually, before I jump into these equations, right here, what I'd like to do is draw plots of acceleration, or the components of acceleration, velocity, and position, if you will. So let's look at what's going on. So look, if you look at my forces, the components of forces that are going to cause an acceleration, right? I have an acceleration in the e hat one direction. So the components of force which cause that acceleration are the components of the forces in the e hat one direction. So I've got a portion of the weight in the e hat one direction. So here's that component of the weight in the e hat one direction, right? That little piece right there. And then I also have the friction in the e hat one direction, which is this piece right here. And these two forces have to add up to something that's going to produce that acceleration. I said that acceleration is in the positive e hat one direction because the package picks up speed. So therefore, this component of the weight has to be bigger than that friction force. Perhaps I've drawn these vectors out of scale. So this force right here, again, this component of the weight has to be bigger than the friction force to get that acceleration down the ramp. Notice that both these forces are constant, right? This component of the weight is constant, and the friction force is constant. The friction force is constant because we're sliding, so we got kinetic friction. And that kinetic friction is equal to mu k times that normal force. That mu k is a constant. That normal force, it's going to equal to the perpendicular component of the weight, which is not changing. So that normal force is constant. So therefore, this friction is constant. All right. So we are going to have a constant net force in the e hat one direction. Therefore, we're going to have a constant acceleration, constant acceleration in the positive e hat one direction. Right. Just to think ahead of what's going on. So as we draw these pictures of position, velocity, acceleration, again, this is to help me wrap my mind around things that are happening. My acceleration is going to be a positive constant right here. Right? So if acceleration is a positive constant, then velocity would be increasing at a constant rate. So velocity starts off right here. So velocity is going to start off right here at VB. So it's going to increase linearly like so. And in the meantime, the position, what's the position doing? The position starting off at s equals 0 down here. And since velocity is growing linearly, in other words, since the velocity is increasing, the slope of this position curve should be increasing as well. So I guess this curve will be, it's actually parabolic, since the integral of a linear function is a parabola, like so. And this block is going to continue going until it reaches the bottom of the ramp. The bottom of the ramp is a distance L down. So as soon as S gets to this distance L, that's going to be the time at which we hit the wall. That's what we're after, right? So to find this time at which we hit the wall, we have to find out what time, or the time t for which this parabola reaches a distance L. That's how we're going to solve the problem. We're going to find where this parabola hits this distance L. And then once we know that time, we can go back over here for an expression for velocity. We can find out the speed at that particular time tf. So that's how we're going to solve the problem. I like writing these little graphs here, these plots, so I can map out a strategy for solving this problem. Again, just to repeat, I can find an acceleration that's going to be related to the balance of those two, or imbalance of those two forces, the tangential component of the weight and the friction. It's going to give me some net constant positive acceleration. I can integrate that to get an expression for this component of velocity as a function of time, which is just going to be a straight line. And I can integrate that to find this position, S, as a function of time. And when that position reaches, position is going to start at s equals 0, and when it reaches s equals L, which is given to us, that's the time at which the block hits the bottom. And I can take that time, put it back into my expression for speed, and find the speed at which it hits the bottom. So that is the whole problem sort of laid out in front of me with these plots. I really like that. way of thinking about the problem, getting the big picture before I start writing equations. All right, so now it's time to start writing equations of motion. Let me come back up here again. Again, the way I write the equations of motion is I want to write some mathematical expressions or symbolic expressions based upon what I see in the free body diagram. Essentially, this free body diagram is F equals ma, right? I want to sum all these forces right here and set it equal to mass times acceleration, right? Here's the left-hand side of F equals ma. Here's the right-hand side of F equals ma. Here's the ma. So let's start with the E hat 2 component. This is a component perpendicular to the ramp. So in the E hat 2 direction, I've got a normal force. There we go, the N. And I've got a component of the weight, minus mg cosine theta, right? So N minus mg cosine theta. So those are the sum of the forces in the E hat 2 direction, or the direction perpendicular to the ramp. So this has to equal mass times the E hat 2 component of acceleration. But notice the acceleration is all in the E hat 1 direction, right? There's nothing in the E hat 2 direction, so on the right-hand side, this equation for the E hat 2 direction, I put a 0. There's 0 acceleration in the E hat 2 direction. And then, of course, well, this kind of tells me something. Remember, I needed that normal force in order to characterize friction. So this essentially tells me what the normal force is, right? These two terms right here have to add up to 0, so therefore the normal force has to be equal to mg cosine theta. And that's a constant. Cool. So I got something from the E hat 2 direction. Next I go to the E hat 1 direction. And again, we should be looking at the free body diagram. So let's go back up to the free body diagram. I've got this component of the weight, mg sine theta. I've got the friction force. And those two have to add up to ma in the E hat 1, right? So that's what I express here symbolically. Again, there's the the tangential component of the weight minus the friction force equals mass times acceleration. And I'm going to refer to this equation again, so I'm going to call it equation number 1. Going a little bit further, I notice that the package is sliding. I said this before. The package is sliding down that ramp. Those two surfaces are rubbing against each other. It's sliding, right? So that friction is kinetic friction. And whenever we have kinetic friction, the expression for that friction force is rather simple. Friction force is mu k times the magnitude of that normal force. And we already solved up here the magnitude of the normal force, mg cosine theta, so I'm going to substitute that in. So there's my expression for friction. Now what I'm going to do is I'm going to take this expression for friction and I'm going to put it into equation number 1. Where's equation number 1? It's right up here. So there we go. Mg sine theta, there's my tangential component of the weight. Here's my friction, mu k mg cosine theta. This has to equal mass times acceleration. I'm going to refer to this again too, so I'm calling that equation number 2. So before we go on, let's remember the grand plan. The grand plan was depicted in this set of plots right here, right? We wanted to find the acceleration so we can integrate that to get the velocity, and integrate that so we can get the position so we can match that boundary condition at a distance L down the ramp to get the time, and then to come back here to velocity, get the speed. But what we want to do, that first step, that next step, is to get the acceleration. I've got an expression down here. Where'd it go? Here's an expression with acceleration in it. And everything in this expression, except for the acceleration, is known, right? I know that mass, gravity is always, g is always given, theta is given, mu k is given, so I can solve this expression for that acceleration. And everything else will be quantities that are given. So therefore, I can solve for A. A will be g sine theta minus mu k cosine theta. So there's that constant A. That constant A has to be positive by the assumption that we made for this problem. And I call that previous equation 2, and I'm not sure if I'm going to need that. I'm calling this one 2.5. Right, so there's our acceleration. What we want to do is take this acceleration, we want to integrate it to find velocity. I'm writing velocity as a v in the E hat 1 direction. So my v is the time integral of A. So there's our expression for A right in there. Now if I ask you what the integral of this, what are you going to say? Take a second, think about it. What's the integral of that thing? I'm giving you time here. Might want to pause. What's the integral of that thing? Well, you might be tempted to say that the integral of sine is minus cosine, and the integral of cosine is sine, right? That's how you integrate these trigonometric functions. But be careful. I'm integrating with respect to time, not with respect to theta. In this problem, theta is constant, right? Theta is just the angle of the ramp. The angle of the ramp is not changing. So all this stuff that's being integrated is just a constant. So the integral is just as simple as can be. It's just this constant g times sine theta minus mu k cosine theta times time, right? Again, all this is just a constant. And then I get this constant of integration too, I call C1. Now, to find that constant of integration, what we're going to do is we're going to look at the initial condition. We know that that speed, that component of velocity at time equals 0 has to be equal to VB, right? The block or the package was delivered to the top of the ramp at a speed VB. So at time, what I'm calling time equals 0, when the block is sort of released at the top, it has a velocity, it has a speed VB pointing downward. So I take this expression that I have for the V, and I don't feel like writing out the sine theta minus mu k cosine theta over and over again. So inside the square brackets here, you take that stuff. So I take that constant and multiply it by 0 because I'm looking at time equals 0. Adding in the constant of integration, all that has to equal VB. But if I have the t equals 0 term right here, then this whole piece right here goes away. And all I'm left with is C1 equals VB. So now if I take that and substitute it into my expression for V, here's my V as a function of time. It's g times sine theta minus mu k cosine theta times t plus VB. So there's my expression for V. And that's exactly what I run, right? V is some linear function of time. Time equals 0 starts at VB, and it's growing. It's exactly like what we said it should be in this plot over here, right? It's that straight line right there. There's my expression that I just derived symbolically. Let's return to what we had. So now what we're going to do is we're going to take this expression for the velocity, and we're going to integrate it for position, right? I'm writing the position, or at least the component of the position, as this symbol s. S is going to be the time integral of v. I take my expression for v in there. That's just this. That's what I found before. Integrate with respect to time. Again, it's a fairly simple function of time because this stuff right there is just a constant, right? The VB is just a constant right here. So when I integrate, I get this quadratic piece. I get a linear piece. So the quadratic piece is the time squared in there. The linear piece is just the time. And I get another constant of integration. To find that constant of integration, again, I look at the initial condition. At time equals 0, this function s at time equals 0 should be 0, right? I started at the top of the ramp, which was at s equals 0. So that's what I'm doing. So once again, this first term I'm multiplying by 0 since I'm looking at time equals 0. This one goes away. The second term, I got VB times t, but again, I'm setting t equals 0. So this one goes away. All I have left, which is C2, and C2 has to be 0. So my expression for the position is just this piece right there. Nice. All right, so let's go back down to our grand plan. We have this function s as a function of time, so position is a function of time, and we want to find the time at which this s is equal to L, right? So we're going to go back up. We're going to take our expression for s, and we're going to put t equals tf in there, and that has to be equal to L. So there's tf, where everywhere there was a t in that position function. And again, the package hits the wall immediately after it travels the distance L. This is exactly what this mathematical expression says. We're going to solve this expression for the TF, right? Everything in this expression is known except for the TF, right? We know the G, we know the theta, we know the L, we know the mu K, we know the VB. So we should be able to solve for the TF, right? So how do we do that? Let me take this expression right here and just write it a little bit differently, maybe a little more compact, maybe a little bit easier to see when you write it this way. Notice I've taken all the stuff in the square brackets and I've just sort of represented by the square brackets here. I don't feel like writing that. Notice this expression we have has something times tf squared plus some constant times tf plus some constant equals 0 if I bring the L over to the other side. This is a quadratic equation. Right? A quadratic equation. We know how to solve a quadratic equation. You did this in elementary school, right? In other words, if I call this constant in front of the tf squared, if I call that a, again, it's just a constant. If I call this coefficient in front of the tf, I call that b, and call this constant out here c. Notice that the minus sign is in the c, right? So c equals minus L. Then the roots of this equation, then, in other words, the values of tf, which solve this thing, would be given by this expression, right? This is the quadratic formula, negative b plus or minus square root of b squared minus 4ac all over 2a, right? That's how we do, that's how we solve those things. You did this, again, in grade school, right? So in particular for this problem, the time at which it hits the wall is going to be negative b, so negative vb right there, plus or minus the square root. I got the square root right here, something up to the 1/2 power. I got that constant right here, vb squared, minus 4 times a times c is what comes next, right? I get 4 times 1/2, which is 2, times a times c. The a is the g times that stuff in the square brackets, so there's the g times the square brackets, and I got the L sitting there too. And you might say, well, this is minus, why do I have a plus there? But remember, the c was minus L, so that's why I have the plus. So there's that stuff at the top, b squared minus 4ac square root, and dividing by 2 times a is this stuff right there, so 2 times that, again, 2 times 1/2 is 1, so I get that in the denominator, and there's my expression. That's my TF. But you got to be careful. That's not really all of TF, or not all of that's TF. I should say it that way. Because remember, here I have a plus or minus, right? So really there's 2 values of TF which makes this thing work, right? One with the plus, one's the plus solution, and the other one's the minus solution. So really, quadratic formula gives me 2 solutions right here, but I'm looking for just one time, right? So what does that mean? So we're going to have to make sense of it. So remember, VB is the speed of the block or the package at the very top of the ramp. VB is positive. G is a positive constant. L is just the length of that ramp. It's positive, right? And the stuff in the square brackets, that was the sine theta minus mu k cosine theta. Sine theta minus mu k cosine theta. Where have we seen that before? Is it down here someplace? Right. I need this total force to be positive in order to get a positive acceleration. So the sine theta minus mu k cosine theta, that has to be positive as well. Let's come back up. So the denominator is positive. So this problem only makes sense if TF is positive, right? Right? I want to know the time in the future that the block hits the wall. I don't want to know a time in the past where the block hits the wall. And notice if we look at my expression right up here, if you look at the expression, if we use the minus root, so if we have minus here instead of plus, just a minus, I have a negative here, and all the stuff inside the square root, that's positive. So let's take the square root, that's a positive number. So if I have a minus sign here, then this time, and of course the denominator is positive, then the time is going to be negative. That doesn't make sense, right? So we don't want to use that negative root. So let's not use that one. Instead, we'll use the positive root. So if we take the positive root, notice that the term inside the square root right here, it's got a VB squared and then plus something. Right? So the stuff inside the square root is something bigger than VB squared. So when I take the square root of this thing, I get something that's bigger than VB. So I got minus VB plus something that's bigger than VB. So if I use the plus root right here, I'm going to get something bigger than 0. So it's the plus root that makes sense. The plus root is looking really good to us. So that's the one we're going to choose for our answer. So here it is. This is our answer for one of the questions we asked. This is the time it takes, the one with the positive root. This is the time it takes for the block or the package to reach the end of that ramp and smack into the wall. Whenever I have an answer, according to the problem-solving checklist, I put a box around that answer to say, this is it, this is special, this is what I'm after. So I did put a box around it. Whenever you do get an answer, it's very important to check the units. I got this complicated expression right here. It's very easy to make a mistake somewhere along that process and screw it up. So I think of this unit check as a way, at least one way of trying to find mistakes that one makes. If the units do check out, doesn't mean you necessarily got it right, but it can easily find mistakes. So let's check it out. So TF, what's that? That's the time at which it hits the bottom. So this thing should have units of time. So let's go through this piece by piece. So on the right-hand side of the equation, I've got a VB. That's the speed of the package at the very top. The speed is a length divided by time, right? It's a meter per second. It's a mile per hour. It's a length divided by time. So that's the VB. I'm adding to it a bunch of stuff inside the square root. What goes inside the square root? Inside the square root, I have a VB squared. So VB was a length over time, so VB squared is a length squared over time squared. Then I got 2 is unitless, G has units of length per time squared, so I write that down right here, length per time squared. L is a length, like so. The stuff inside the square brackets right here. First I have a sine of theta. Right? If I have a triangle, then the sine, a right triangle, then the sine of one of those angles is the opposite side divided by the hypotenuse. It's a length divided by length, so that's unitless. Similarly, the cosine is unitless, right? It's the adjacent side divided by the hypotenuse. So that's a length divided by length as well. Mu k is unitless. If you go back and look at that expression for that friction force, the friction force is equal to mu k times the normal force. So mu k would be a force divided by a force. So that's unitless as well. So the stuff inside the square brackets is all unitless. So I represent unitless things by the number 1. Okay, so what do I have inside the bracket? Oh, I forgot the denominator. Again, the stuff inside the bracket is unitless. In the denominator I have a g, so that's a length over time squared. So let's look at these terms again. So on the outside, I've got a length over time, and right there, there's the length of time. Inside the square roots, I have a length over time squared, plus I got a length squared over time squared, and then I have a plus length squared divided by time squared. So everything inside the square root is length squared over time squared. And again, I'm dividing by length over time squared. So now I take this square root, and that just gives me a length over time. So I got a length over time plus a length over time, which is a length over time. I'm dividing by length over time squared. So notice that this length will cancel out that length. And what I have is a 1 over time divided by a 1 over time squared, which is a time, which is exactly what we wanted. Whew. So the units of this big messy expression right here all works out. It turns out to be a time, which is exactly what we wanted. So I have some confidence in this answer. You know, this little unit check doesn't guarantee you got the right answer. I might have missed a factor of 2 someplace. I don't think I did, but it's looking positive. So I want you to definitely put in a unit check. Now what we want to do is we want to answer the second part of our question. Remember, we also wanted to find the speed of the block when it hits the bottom. Right now it's really easy. So I already have an expression for speed. That was given by equation number 3 on page 2. I'm not even sure I can find that. Here it is. Equation number 3 on page 2 is this, right? There's my speed as a function of time. That speed as a function of time was this linear function right there, which looks like that. So if I stick a TF into that expression, then I get the VF, right? Stick the TF into the expression, I get the VF. And this might sound messy. I got this thing, I'm going to stick the TF, and the TF was kind of messy, but really it's not so bad, because remember, this expression for TF in the denominator had a G times sine theta minus mu k cosine theta. That expression for the V also had a G times that stuff in the square bracket, the cosine theta minus mu k sine theta. So this stuff right here, multiplying the TF, is exactly what was in the denominator of the TF. So when I multiply these two things together, it's rather simple, like so. And you'll notice I had a minus VB coming from the TF right there. There's the minus VB. Remember that thing? And then this expression for the velocity has a plus VB at the end. So therefore, this thing is going to cancel out that thing. And what we have left is the stuff inside the square root. So there's my VF. Again, you should check your units. Maybe it looks like I forgot to do mine over here. But again, this is V. So let's go ahead and check those units real quick. The VB, again, was a length over time. So VB squared is a length squared over time squared. I'm adding to that a 2. 2 is unitless. G is a length over time squared, which I've written right here, times a length. So I take these two terms, they're both length squared over time squared, so I got length squared over time squared underneath that square root. Take that square root, I get a length over time, which is exactly what I want, right? The speed here, the speed at which we hit the wall, is a length over time, so I've checked those units. Good, I didn't forget it. And that's that. We're done. So that's it. We found both things that I have asked you to find. We've solved a fairly complicated problem. Again, I want you to understand every single step very well. So go back over this thing. Make sure you understand it perfectly. Make sure you can do this on your own if you want to. In fact, try it. Do it on your own again and see if you can get this thing to work out without referring to the video. Of course, you can come back to the video if you get stuck. But I want you to know how to do this on your own. And when you can do that, pat yourself on the back because that's an accomplishment. Okay? But I don't want you to stop thinking. There's a couple more things I want you to think about this problem. All right, so there is the answer. Let's go back to the problem statement itself. So here was the problem statement itself. We had this ramp. We were asked to, given these two things, we have to find the VF and the TF. And when we went about this, we did a few things. So first of all, notice when we worked this thing out, we chose vectors that are aligned with the ramp. So we had an e hat one direction, which is tangent to the ramp, and e hat two direction, which is perpendicular to the ramp. Why did I do that? I want you to think, why did I do it that way? And maybe the best way to realize why I did it that way is for you to try to work on this problem a different way. In other words, let's suppose I asked you to work out this problem. Instead of using e hat 1 and e hat 2, let's suppose you use the standard I and j, where I is horizontal and j is vertical. Why don't you try setting up the problem that way? I'm not going to ask you to go through the entire problem that way. Just go through the problem where you just solve for the acceleration, right? And what I mean is, what I mean by solving the problem with the I and the j, I'm going to ask you to take this free body diagram, instead of decomposing the weight and the friction and the normal force in terms of e hat 1 and e hat 2 directions, decompose this all in terms of the I hat and the j hat. And you'll find that the W is quite a bit more simple, right? The W is just in the minus j hat direction, but the normal force and the friction force are going to have both I and j components in them. And if you look at the mass acceleration diagram, you know that the acceleration is tangent to the ramp still, but that acceleration tangent to the ramp is going to have an I hat component and a j hat component. So work out this problem in the I hat and the j hat components, and then try to solve for the acceleration. Remember, when we solved for the acceleration, it was a really simple task. But you'll notice if you have it all in the I hat, j hat direction, it's going to be a little more work. But I want you to try it. I want you to do it so you can appreciate what we did here by setting up the e hat 1 and the e hat 2 directions like we did. So that's the first thing I want you to think about. The second thing I want you to think about is this assumption we made. This assumption we made, we said that the block hits the wall at a speed faster than the block was, or the package was at the top of the ramp, right? So it picked up speed on its way down. What if I remove that assumption? Let's not assume that this is the case. Maybe the block slows down as it goes down the ramp. Let's assume, though, it does not get stuck, Okay, let's assume that it makes it all the way down to the bottom, but what if the block slows down when it gets to the bottom? How does my analysis change? I want you to think about those two things. That is, what if we change the coordinate system to an I and j, and what if we get rid of this assumption that the block speeds up as it slides down? What if it actually slows down? All right, I want you to think about those two things, because it opens up your mind to some problem solving here in an important way. So please do it. Don't slough it off. Don't actually just think about it. Start working it out and see how it affects the solution. All right? So I'm signing off. Over and out.